Hello, everybody. Today I'd like to describe some corollaries of Lagrange's theorem. So, if you remember, Lagrange's theorem says that if G is a finite group and H is a subgroup, then the size of the subgroup H divides the size of the group G. Okay. So today we're going to focus on some corollaries of this important theorem. Okay, so the first corollary is that if G is a finite group and A is any element in the group, then the order of A divides the size of the group G. Remember, the order of A is the smallest integer n such that A raised to that power is equal to the identity. So in symbols, the order of A is defined as the smallest integer n so that A to the power n is equal to the identity. Okay. And I guess we're looking at positive integers n. And you'll recall that the order of an element is the same as the size of the subgroup generated by that element. Okay? So this subgroup, the subgroup generated by A, is a subgroup of G. So Lagrange's theorem says that the size of this subgroup generated by A divides the size of the group G. And the size of this subgroup generated by A is nothing else than the order of A. So immediately that gives us this, this corollary down below at the bottom of the page. Let G be a finite group and let A be an element of the group. Then A raised to the power, which is the order of G, is equal to the identity. Okay? So if you have a finite group, if it has 17 elements, then any element in that group, when you raise it to the 17th power, you automatically get the identity. What's the proof? So since the order of A divides the size of the group by the corollary at the very top, we can write the size of the group as the order of A times something. That's what it means for the order of A to divide the size of the group G. We can write the size of the group G as the order of A times some number. Here we've written that number as K. Okay, so let's compute A to the size of G. We're hoping to get the identity. Well, that's just A to the power, the size of A times K. And then I can sort of factor this. That's A to the power, the order of A, all that to the power K. But we just saw, by the definition of the order of A to the power, the order of A, is equal to the identity, right? That's this definition up here. Okay. The order of A is an integer such that A to that power is equal to the identity. So this is just the identity to the kth power, which is the identity. All right, fantastic. We've seen that Lagrange's theorem implies that the order of any element divides the size of the group. And therefore, this corollary at the bottom follows, which says that in a group that's finite, take any element, raise it to the size of that group, and you get the identity. All right. Let's talk about this corollary in the middle here. So we're hoping to show that if G is a group whose size is a prime number, then group G is necessarily cyclic. Okay? So some example prime numbers are, of course, 11 and 13 and 17. So if you ever find a group that has size 11, or size 13, or size 17, for example, you automatically know that it's a cyclic group. It's generated by a single element. Okay, here's the proof. Let G be a group whose size is prime, and let A be any element of that group that's not the identity. We're going to show that A generates this entire group, cyclic group of prime order. Well, we'll show that A generates this entire group of prime order, and therefore that group is cyclic. Since A is not the identity, the order of A is not 1, right? The identity is the only element where that element to the first power is the identity, right? The identity is the only thing that's the identity. And we proved that identities in a group are unique. So if you're not the identity, then you at least need to square yourself or cube yourself, etc., until you get back to the identity. The order of A, which is not the identity, is not 1. Okay. By our corollary at the very top of the page, we know that the order of A divides the order of the group, which is a prime number. So we have some positive number bigger than 1 that divides a prime. Well, primes are defined as being the only numbers that divide a prime are 1 and the prime number itself. So if the order of A is some positive number bigger than 1 that divides a prime, the order of A must be equal to that prime. In other words, this implies that the order of A is equal to the size of G. Alright, so then it follows that the cyclic group generated by A, namely all things of the form, A or A squared or A cubed, ... all the way up till you get to the back to the identity. It follows that that set has this given prime number of elements, so it's equal to the entire group. And by definition, since the group is generated by a single element A, that's what it means for the group to be cyclic. Down below, I've listed 2 examples. Any group of size 7 is cyclic, and therefore isomorphic to the integers mod 7. 11 is also prime. Any group of size 11 is cyclic, and also isomorphic to the cyclic group Z mod 11. All right, wonderful. Let me end by discussing Fermat's little theorem. So Fermat's little theorem is one of the first results that you start using in number theory. Number theory includes a study of prime numbers as the main objects. So Fermat's little theorem says that if P is prime and A is any integer, then A raised to the power P, mod P, is the same as A. Okay, so let P be prime, let A be any integer, then A to the pth power, mod P, is equal to A. Let's try this a little bit. So 7 is going to be our prime, and here I've raised 4 to the 7th power. So 7 is our prime P, and 4 is our integer A. Alright, 4 to the 7th power is not equal to 4. But what this is saying is that 4 to the 7th power mod 7 is equal to 4. You see that? 4 to the 7th power, here I can use my mouse. 4 to the 7th power right here, mod 7 is the same as 4. Let's try 5. What is 5 to the 7th power mod 7? This theorem is telling us that it should be 5. And it is. 5 to the 7th power mod 7 is 5. Let's try 6. 6 to the 7th power, mod 7, is 6. Even though it's this huge number, 6 to the 7th power is this huge unwieldy number, right? Oh my gosh, what can you say about this number, 6 to the 7th power? Well, surprisingly, its remainder, when divided by 7, is 6. So a to a prime power, mod that prime, is always a. Back to our notes. That's what we're trying to prove. P is a prime, a is an arbitrary number, a to the pth power, mod p is congruent to a. Proof. Alright, so it suffices to check this for the different congruence classes mod p. Everything in Fermat's little theorem up above is mod p. So to check that, we only need to check it for the different congruence classes. 0, 1, 2, ... all the way up to p minus 1. The next comment is that the case a equals 0 is clear. 0 to the pth power is always 0. We're handling the case a equals 0 separately, just because in the next lines we'll prove all other cases, a equals 1, 2, ... up to p minus 1, using a slightly more complicated technique that doesn't work for a equals 0. Alright, so let's consider all other cases. A is some number from 1 up to p minus 1. What is u of p? U of p is the group of units mod p. It's all the numbers from 1 up to p minus 1 relatively prime to p. Since p of prime, u of p is the entire set 1 up to p minus 1. Because every number up to a prime is relatively prime to that number. In symbols, for p prime, the group of units mod p as a set is all numbers up to p minus 1. Okay. Not only is u of p a set, it's also a group equipped with multiplication mod p. Okay, so here you can see that for p prime, the size of this group of units mod p is p minus 1. That's explained by this up above. When p is prime, the group of units has p minus 1 elements, 1, 2, all the way up to p minus 1. So we have some group, and we know its size. It's p minus 1. And now, in this group of units, any element raised to the power of the group is equal to the identity of the group, right? That's this corollary right here. In a group, any element raised to the power of the group is equal to the identity in that group. Right now, our group is u of p, the group of units mod p. So any element raised to this power, the size of u of p, is congruent to the identity in u of p, which is 1. Multiplying by 1 doesn't change anything. 1's the identity. Okay, this equality here is just explained because what is the size of u of p? We saw that's p minus 1. So, in total, what do we have? We have that a to the p minus 1 is congruent to 1 mod p. Let's multiply both sides by a. The left-hand side just becomes a to the p, and the right-hand side becomes a times 1, or a, mod p. And that finishes off the proof now of Fermat's little theorem. We had that a to the power p minus 1 was congruent to 1 mod p. Multiply both sides by a to get a to the p is congruent to a mod p. Alright, so this is a beautiful little important theorem in number theory, and it really follows from this group theory fact that A, an element of a group, raised to the power of that group is the identity. And here we're just applying that theorem in the group of units mod P. Let me end with two remarks. Fermat's little theorem is used, for example, to show that some large numbers are not prime. So for example, lots of prime numbers that you might search for are of the form 2 to some large power minus 1. Some prime numbers are of that form, not all. Some numbers of that form are prime, not all. But in any case, these are useful numbers to look for when you're searching for primes. Okay, so 2 to the power 257, some humongous number, subtract 1. Is that prime? I have no idea. Well, you can do some computations. If it were prime, then any number raised to that power should be congruent to itself mod that number. Okay, so P is this number, 2 to the 257th power minus 1. If P is truly prime, any number to the pth power should be congruent to that number A, mod P. But 10 does not satisfy this. You can check what is 10 to that power mod P. What is 10 to the power P mod P? It's not equal to 10. And so therefore, that breaks Fermat's theorem, not breaking the theorem, but just saying that P couldn't have been prime. Because if P were prime, 10 to the p power would have to be congruent to 10. All right, second remark. We showed up above using Lagrange's theorem that a group of prime size has to be isomorphic to Z mod P, right? That's this corollary, which I'll highlight in blue. If G is a group with prime order, prime size, then G is cyclic, and therefore isomorphic to Z mod PZ, where P is that prime. Okay, what can you say if your group has size 2p, where P is prime? Okay. So if your group has size 2p, where 2 is prime, if your group has size 2p, where P is prime, then you're not necessarily cyclic. You're either cyclic, isomorphic to ZP, or you're isomorphic to this dihedral group, the symmetries of the regular polygon with P vertices. So, for example, let's talk about P equals 5. Okay, so 2P is equal to 10. What this is saying is that a group of size 10 is isomorphic to either Z mod 10 or D5. D5 is the symmetries of the regular pentagon. Drawn a pentagon there. So D5 has 10 elements in it. It has 5 rotations and it has 5 flips. Okay? And proving this is a little bit harder than proving the case where the group had size P and was therefore cyclic and isomorphic to ZP. It requires a little bit of elbow grease, a little bit of work, but it's doable with the tools you know. You can check it out, Theorem 7.3 in our book. A group of size 2p, where P is prime, is either cyclic, isomorphic to Z mod 2p, or dihedral, isomorphic to this dihedral group. If I give you a group of, I don't know, size 24 or size 100, which is not prime or not twice a prime, it's hard to figure out what all of the possibilities are for that group. Mathematicians really have figured this out in a satisfying way, but it's complicated and took years of work. All right, thanks for your attention.